no advantage in terms of marks or anything like that. The only advantage would be for you spending less time on the project, possibly. And so let's take a look at the code. Yes, I have this main code here. And so this is kind of the code that's outside my C coder. And so the way I've set it up is I initialize the robot parameters, so I load in numbers for all the parameters. And this is the file that's basically given to me by the company that built that robot. So all the numbers in that file are numbers from the company. I've never verified them, but they appear to be good enough to design controllers with anyway. The lengths look, I think I've verified the lengths, but certainly not any of the masses or inertias or anything. So I have like this Cartesian coordinate system, so I'm starting off, like I said, at x is 50 centimeters and y is 0, like I showed you in the lab. Now that I think of it, I think I might have just had the elbow the wrong way in the lab. Remember I had it set up like this and then didn't look like it was making a square. So now that I think about it, I probably should have just turned the elbow the other way and see if it actually did do a square. Probably would have. Probably just the elbow was pointing the wrong way. And I have a function inverse kinematics. So I have kinematics and inverse kinematics. So I didn't tell you in the class how to do the inverse kinematics. I only showed you the kinematics in the class and mapping from theta to Cartesian coordinates. So inverse kinematics is going the other way. Someone gives you x and y of the end effector. You're supposed to figure out all the angles and angular velocities in the joint coordinates. So I didn't show you how to do that. You can look that up in any robotics textbook. In fact, I think I actually typed in the robotics textbook I got this from inside the code, so you could actually look at that one in particular if you wanted to. But I'm sure you could just find it on the internet anywhere too for a 2-link planar robot. It's such a common example, so it's not a big deal. But anyway, I did not show you how to do that in class, just in case you're wondering. So this is all kind of set up. When I did this code initially, I initially had this code running for like a neural network training to learn how to control the robot. And then to give this code to you, I took out all the neural network code. But I still left kind of little bits and pieces in there left over from my neural network code, and like this is one of them. So like with my neural network, I wanted to run it for like 100,000 times just to make sure my neural network was converging and never diverging ever, right? So I just wanted to run it for a long time to make sure nothing bad was happening. So I'd set up this variable that would be long run, so I wouldn't actually have to save all the data on each time step if I was doing an overnight run. But the way it's by default set up right now is that every single time step you will save all the data. So you'll get a fairly large data file in the end. But then you can graph all your variables in time, so you have a nice thing to look at. So that's why that's in there. And so like I said, here's the code that does the C coder. And like I said, there's no requirement that you use C coder. It's just an advantage in terms of runtime. And it might not even be that for you because it does take time to compile. So maybe the time that it takes to compile totally isn't worth it for you, and you can actually get it faster working in MATLAB, I don't know. But if you do use a neural network, you'll probably want to compile it in C code because then it will make a difference. So basically I'm just running this one function. Because I'm doing C coder, I want the C coder to work just on one particular function that I can set up in C coder. So I'm either calling run robot if I'm doing pure MATLAB, or if MATLAB's being converted into C, C coder creates this function called run robot underscore mex. So in MATLAB, mex means C. I don't know why mex means C, but that's what it means. And then I just basically graph the results, and didn't I animate this too? Yeah, I graph the results and I animate it too, so you can take a look at my little animation. So you might want to keep that, or you might not want to keep it. It might be annoying. It all depends. But I thought it'd be nice to at least see what the robot was doing for you. Did everyone try this out at least? And then here's my function run robot. So it's kind of a strange blend of coding philosophies and syntax, because I'm coding like I'm doing Java and Rachel's coding like she's doing C. but it's all MATLAB, so it's probably really obvious what Rachel's typed in, what I've typed in. But basically, we're just integrating with ODE45. So ODE45 is the integrator. It's a pretty handy integrator. I mean, you can use a different integrator if you want, but it's pretty much probably not going to improve on that integrator. So I'm just integrating over one time step. So I have an input coordinates. I'm integrating, in this case, I think it's for 0.02 seconds or 0.01 seconds, so one time interval. So if I'm doing a 10-second run, it's a really bad idea to put, it's really bad idea to call ODE45 and then put 10 seconds in here. It probably won't work because you're asking the integrator to keep track of what it's doing over a full 10 seconds. Integrators are good, but they aren't that good. So what I do is I call the integrator for like 0.01 seconds or 0.02 seconds, and then I call it again for the next 0.02 seconds, and then I call it again for the next 0.02 seconds. Much more reliable way of doing it. Kind of resets the integrator each time and kind of forces it back on track rather than letting it drift off, which it tends to do if you give it a large time interval. So you'll see that you can put your controller, if it's a continuous time controller like a PD or a PID controller, you can put it right inside this function robot dynamics. So if you have a PID, you're actually integrating your integral term for your controller along with integrating your system states. So it's all integrated all at the same time. But we'll see when we do neural networks later on in the course, we'll see that the neural network output I'll actually just keep constant for that time interval. So if I'm calling something like this, I'll have a neural network, and I'll actually calculate the neural network in this function. I won't calculate the neural network inside robot dynamics. So if this is running at 0.02 seconds, then the neural network will, every 0.02 seconds, the neural network will produce an output. And then the easiest way to do it is just have that output as a global variable. So when it goes inside robot dynamics and takes a look at the neural network output, that neural network output is actually remaining constant for that time interval. So the PD or PID control is changing continuously during that time interval, but a neural network output for a little time interval will just be a constant value. It'll just stay the same thing. And then you can see that you can see that I've definitely left a few hints in here of what I would want you to do if you were running a neural network. So, I'm keeping track of root mean squared error as I go around this square trajectory, and I'm kind of assuming I'm going over and over again, and I'm kind of keeping track of how that error has changed. Well, if I'm running a neural network, that makes sense because probably the error will get reduced each time I do the square. The neural network should learn how to control the system, and the error should go down to like 0 eventually. But if you're not running a neural network, then there's probably no point in using this variable at all because you're probably just going to go around the square once and see how it worked. So you wouldn't keep track of the root mean squared error as you went around. So I'm keeping track of the weights in my neural network. Well, I have this commented out because I don't even have a neural network in this code, but that would be the other thing you do if you're using a neural network is you keep track of the size of the weights, make sure the weights aren't going off to infinity in your neural network as you go around this thing. But like I said, if you're not doing a control with a neural network, you're probably just going to go around the trajectory once, and there's not going to be this idea of keeping track of the error over cycles or anything like that. So the whole concept of cycles in this code would probably be not too useful to you. So we can take a look at the robot dynamics. So I have a trajectory generator here, square trajectory, so it's extremely clunky trajectory generator I'm using, just like accelerating and then decelerating, accelerating, decelerating, accelerating, decelerating, going around in a square. So it's very, very primitive. You're more than welcome to add in your more sophisticated trajectory planner in there if you want to do something a little more interesting than a square. So I kind of giving you the hint here, you might want to try out different controllers. So if you do try out different controllers, you might just like to have a little variable in your main program that tells you which particular controller you're using for a particular run. So I've called this one use proportional control of gravity feed forward. So you can see in this particular control, it actually knows the gravity term. So this is technically a nonlinear control because I'm canceling out gravity, if you will, so that I don't have to have an integrator. Otherwise, if I didn't do this, I'd want to have an integrator in there to make sure that it didn't sag due to gravity. And then I just have this proportional control. So this isn't even a PD control. I don't even have a velocity term in here. So this is a very primitive kind of control term, right? So this is just based on position error, not even on velocity error. So it's not a particularly good control, but I just thought I'd give you a control that's actually working, even if it's rather simple. You can see that I'm assuming I know this term here. So the gravity term, I'm assuming I know the gravity term. So I'm actually using that in the control. So that actually appears here. So I kind of just copied and pasted it from the code that produced my robot equations. But you can see that, I have this function, find acceleration, find accel. So this is what was produced by my MATLAB symbolic math code. So I derived the equations, well, I didn't exactly by the way, because I didn't start with Lagrange's equations. But anyway, I calculated what my equations should be using MATLAB symbolic math, and then created this MATLAB function, find accel. So this just gets those link accelerations, so that that has to be the output of the integrated function. So the idea here is, this is what ODE45 wants. ODE45 wants derivatives, right? So it can integrate. So the whole idea here is I have a system in form of x1 dot equals x2. So my first line of derivatives is just x2, and then my second line of my dynamics is x2 dot equals, and that's where you get all those nonlinear terms and everything. So that's the actual accelerations in my x2 dot. Okay. So the first one is simple because it's just x1 dot equals x2, and then x2 dot equals this. So, anyone have any questions about the code at all? So if you haven't tried implementing a bit more sophisticated control like a PID or an LQR control, make sure you give that a go next week before the next lecture, because once you've done that, then it's pretty easy to understand what I'm getting at in class and what I'm talking about, and you'll ask really good questions because you'll have tried this out already, and you'll kind of know some of the issues that are involved with trying to get a controller to work. So if you don't sit down and try this code out at this point, it's going to be much harder to get things out of the lectures and understand what you have to accomplish for the project, and what's really important, and what kind of questions to ask me and stuff like that. So definitely give a PID control an effort before the next lecture, or an LQR control, and see if you can get it working. Does anyone have any questions for me for the code? So doesn't look like there's any questions, so I'll pass out your quizzes, and then you can go. But this is my chance to learn everyone's names, so I'll do it the slow way. But I know Josh, and who's Nathan? Yeah. Nathan. You don't want me to call you OSC, right? What do you go by? Shay. Shay. That's what I thought. That's the one. Press. And who's Nicholas? Yeah. Right? Nicholas. And Quinn. Sam is over here. Salad. And Leona here. Great. Shadi. There you go. The class average was 50%, by the way. There you go, Emily. I guess it was a hard quiz. Sorry about that. Didn't necessarily set out to make it a really hard quiz, but it turned out to be a really hard quiz. And we'll see you on Monday.